Alright, so this is example unit C3, page 9, last example of unit C3. This is flow rate measurement of the pipe. Suppose you have a pipe system, you want to know how much flow rate do you have inside of the pipe. So your purpose is to determine Q, flow rate. Okay? So you're going to usually pick up multiple devices. One of them is called venturi meter. Venturi meter is a meter which comes with a reduced cross-section slope, and then this reduced cross-section accelerates the flow, so induce the lower pressure here. So if you determine the pressure difference between 0.1, 0.2, 0.1 is obviously higher pressure, 0.2 is lower pressure, somehow you can determine the flow rate. I think we looked at this one in unit, I think, B3. Can we determine the pressure difference between those 2 points by using some kind of device? That device is called U-tube differential manometer. Okay? So suppose this is that kind of device, U-tube differential manometer, or could be a digital pressure transducer, but any kind of device here, you're going to purchase that device which is suitable for this case. Let's take a look at this example problem. This is a kerosene. Kerosene is lighter than water, so specific gravity of kerosene is 0.85. This one is flowing through the venturi meter. Okay? Then you already know the range of flow rates. Flow rates will be expected to be between those two ranges, 0.005 to 0.05 cubic meter per second. So this is a pipe system that actually you expect to have this range of the flow rate already. So let's determine the range in pressure difference P1 minus P2 needed to measure these flow rates. So this is the design problem. Based on the condition given, you are going to design your device. So if this is differential U-tube manometer, what kind of fluid do you want to use? How big your U-tube shape should be? That kind of thing. In order to determine, you have to determine the pressure difference range corresponding to this flow rate range. Okay? So let's take a look. So obviously this is the problem based on Bernoulli's equation. So suppose if Bernoulli's equation is applied between 0.1 and 0.2, you end up having P1 plus 1/2 rho V1 square plus gamma Z1 is equal to P2 plus 1/2 rho V2 square plus gamma Z2. This is a horizontal pipe, so Z1 equal to Z2. So this term drops off. So you're going to have P1 plus 1/2 rho V1 square is equal to P2 plus 1/2 rho V2 square. Okay? This is equation 1 coming from Bernoulli's equation applied between 0.1 and 0.2. Then, of course, continuity. You can apply continuity between 0.1 and 2 also. Q1 equal to Q2. In other words, Q is constant throughout. So this gives you cross-section area A1 times velocity V1 is equal to cross-section area A2 multiplied by velocity V2. This is equation 2 coming from continuity. So what we can do is we can combine those two equations. You're going to have flow rate Q. Q is equal to A1 B1, actually B1 A1, which is equal to B2 A2. So you can have two similar kind of equation of the flow rate expression, but suppose if you choose this one, B2 times A2, you're going to have this kind of equation. Equation is square root 2 times P1 minus P2 rho 1 minus A2 over A1 square multiplied by A2. Okay. So this is the equation of flow rate. Now obviously you can have similar equation, which is square root of very similar thing times A1 also. Okay. So here's my challenge for you. Do it yourself. It's a fairly simple manipulation of the equation starting from those two equations. Solve for Q in terms of cross-section area A2, so in other words this is B2. And then in terms of cross-section area A1, so this is essentially B1. B1A1 or B2A2 is going to give you the flow rate Q. Okay? So this is the equation given in note. This is something I can easily pick up as a quiz problem. So, okay? So please do it yourself to make sure you understand it and you can derive those kind of equations. So let's use this one to solve this problem. Okay? So let's pick up this. So let's pick up this problem. Q equation. Q equal to A2 square root 2 times P1 minus P2 rho times 1 minus A2 over A1 square. I'm going to change the form of this equation. Let's solve this for P1 minus P2. Okay? So P1 minus P2, this is the pressure difference, is equal to flow rate Q square times rho 1 minus A2 over A1 square divided by 2 times A2 square. So it's just a change of form of this equation. So range of Q is known, 0.005 to 0.05 cubic meter per second. So this is the range of flow rate you expect to have. And one more information. Area ratio A to A1. This is fixed. By the way, if you take the ratio of the area, if it's a circular cross section, it is going to be exchanged into the ratio of the diameter square. Okay? So area ratio is diameter ratio square. This is something you need to remember. So this is 0.06 meter at the throat section. This is 0.1 meter of the pipe internal cross section square. This is 0.36. Okay? Also, specific gravity. This is kerosene, specific gravity. So density of kerosene can be given by Sg of kerosene multiplied by density of water. So this is 0.85 times density of water in room temperature, 1,000 kilogram cubic meter. Really nice number to remember. So density of kerosene is 850 kilogram per cubic meters. Okay. All right. So these are all conditions. So therefore, okay. For the case of Q equal to 0.005 cubic meter per second, so this is the lowest possible flow rate you expect to have. How much pressure difference? P1 minus P2. Let's plug into this equation. So flow rate is 0.005 cubic meter per second. This thing is square. Density is 850 kilogram per cubic meters. 1 minus 0.36 square. Okay, area ratio is this. 2 times cross-section area is pi over 4 times 0.06 meter square. Okay, so this is going to give you the pressure difference, 1160 Newton per meter square. So this is 1.16 kilopascal. Okay. So what about the case of a maximum flow rate you expect to have, 0.05 cubic meter per second? If the flow rate becomes this high, what is the P1 minus P2? Flow rate is this one. Flow rate, this is 10 times bigger flow rate. Then square term comes in. So P1 minus P2 is going to be 100 times larger, right? So this is going to be 116 kilopascal. Okay. So here's the conclusion. The problem is asking you what kind of range of pressure drop you need to expect. So this is the question of you picking up proper device that is capable to measure the range of pressure drop between 1.16 to 116 kilopascal. So the device. This device could be digital pressure transducer or could be YouTube differential tube manometer. Either one is fine, but the device needs to be measured, needs to be capable. Okay, sorry, so the device needs to be capable to measure delta P, pressure difference, which is P1 minus P2, in the range of 1.16 kilopascal to 116 kilopascal. Okay? This is going to determine what type of YouTube manometer you need to pick up with. You know, size of the YouTube glass tube shape, and also what is the gauge fluid you put inside also. Okay? Alright, that's it.